In this video, we're going to look at partial fractions where the denominator contains distinct quadratic factors without an x term. Now, we've already looked at what happens when we have irreducible quadratics in the denominator. However, those were general quadratics. Here we're looking at a very particular case. We're looking at when there's only an x squared and a constant term. That's to say that there is no x term in our quadratic. So we want to do a partial fraction decomposition here. So let's write it out. 1 over x squared plus 4 into x squared plus 9. So we know that this is going to turn into two fractions. The first has a denominator of x squared plus 4, and the second has a denominator of x squared plus 9. Now what goes on top? Well, according to our partial fraction theorem, the degree of the numerator should have a degree less than that of the denominator. And what we usually do is we usually put a degree which is one less on top, because that covers all of the cases. So if we have a degree 2 on the bottom, we put a degree 1 polynomial on top because that also covers a degree 0 case. However, in this case here, because we don't have an x term in the denominator, there's no need for us to put an x term in the numerator. And I'll show you why. Let's have a think about this function in a slightly different way. Let's think about, instead of x squared, let's just write u. 1 over u squared, not u squared, u plus 4 into u plus 9. Now if we were to break this up as u plus 4 and u plus 9, fractions with those denominators, well, clearly the numerator has to have a degree which is 1 less than the denominator. And since the denominators are degree 1, the numerator should be a degree 0, which is just a constant, a and b. And the reason we can do this is we've just made a substitution u equals x squared. In this case, it's fine, but in our other case where we have x terms, we can't make that substitution because that'll introduce a square root of u, which is very undesirable. But in this case, it's not a problem because there's no x term, so we don't have to introduce the square root of u. So we know now that our numerator can be just a constant, a and b. Alright, so our job now is to find a and b. And we can do this in three ways like we've already seen: equating coefficients, substitution, and the cover-up method. Now I'm going to do all three in this example because it's very similar to what we've already seen, but in some cases it's just slightly different. So let's have a look at the first case where we're equating coefficients. In this case, it's actually going to be the same idea as what we've already seen. So let's make a common denominator on our left-hand side of the fraction. So that's going to be a into x squared plus 9 plus b into x squared plus 4. And all of that is divided by x squared plus 4 into x squared plus 9. And so now we can equate this numerator with that numerator there, because they're the same fraction with the same denominator, so their numerators must be the same. Alright, so what do we have? Well, we have 1 equals a into x squared plus 9 plus b into x squared plus 4. Okay, so let's have a look at the coefficient of x squared. What's the coefficient of x squared on the left-hand side? Well, there is no x squared, so that means the coefficient is 0. And on the right-hand side, it'll come from a times x squared, which has a coefficient of a, and b times x squared, which has a coefficient of b. So that would tell us that a is equal to negative b. Okay, so that's our first equation. And then having a look at the coefficient of the constant term, which is x to the power 0, on the left-hand side it's equal to 1, and on the right-hand side it's going to come from a times 9, and 4 times b. Okay, and that's our equation 2. And then if we solve these two simultaneously, we get a is equal to a fifth, and then b is going to be equal to negative a fifth. Okay, so that's the equating coefficients method. How about the substitution method? Now it starts to change just slightly. Okay, now what did we usually do when we dealt with substitutions? What we wanted to do was we wanted to eliminate all the unknowns, so all the constants except for 1. And the way we would do that is by trying to substitute some value for x which would make this factor 0 or this factor 0. Now, when we were dealing with quadratics, this wasn't always something that we could do because we'd have to jump into the complex world. We'd be dealing with complex numbers because they were irreducible quadratic factors. That's still the case here. However, it's much easier to sub in a complex number here because it's going to be purely imaginary. So for example, if I want to eliminate b, I want to substitute x equals something, which is going to make x squared plus 4 equal to 0. Well, x squared plus 4 equal to 0, that's actually pretty easy to solve. That's just x equals plus or minus 2i. So I can substitute either plus 2i or negative 2i into this, maybe we'll call it star, into this starred equation. So I'm just going to sub in positive 2i, I'll get the same answer anyway. But when I do that, well, on the right hand side there's nothing related to x, so it's just 1. On the right hand side I have a times 2i squared, which we know is negative 4, plus 9, and then b times 0. And so I get a times 5 equals 1, which implies that a is equal to 1 on 5. I can do a very similar thing by substituting x equals 3i in, and that's going to make this, let's change the color, that's going to make this term become 0. So when I do that, the left hand side is still 1. We get a times 0 plus b into 3i squared is negative 9 plus 4. So 1 equals b times negative 5, which tells us that b is equal to negative a fifth. And so we get the same results for a and b, which is a very good sign. Now, what about the cover-up method? This one is a bit different. Let's go back to our fraction here. Let's actually write that. It was 1 over x squared plus 4, x squared plus 9, and that's equal to a over x squared plus 4 plus b over x squared plus 9. Now what we did was we multiplied by the denominator of the fraction involving a, and then we did a limit which set x to some value which is going to make that denominator equal to 0. So in this case, a is going to be equal to the limit as x squared approaches negative 4, because that makes the denominator equal to 0, of x squared plus 4 over x squared plus 4 into x squared plus 9. Now I can cancel these factors here, and I have the limit as x squared approaches negative 4 of 1 over x squared plus 9. Well, what's that equal to? 1 over negative 4 plus 9, which equals a fifth, which is the same result as we had in the previous two methods. If we do something very similar for b, b would be the limit as x squared approaches, well, what makes the denominator 0 in the fraction involving b if x squared was equal to negative 9? So we do that limit, x squared approaches negative 9, of x squared plus 9 divided by x squared plus 4 into x squared plus 9. These are going to cancel, and we have the limit as x squared approaches negative 9 of 1 over x squared plus 4. And this is going to be 1 over negative 9 plus 4, which is negative a fifth. And once again, we get the same results as we did in the previous two methods. So those are three ways that we can decompose partial fractions of this form. So now we actually want to work out our integral. So the integral is a divided by x squared plus 4 plus b, which is negative 1 on 5, over x squared plus 9 dx. And now these are in our standard inverse tan forms. So I have 1 on 5 as the constant out the front. Tan inverse of x divided by 2, but don't forget that we also have to divide the whole function by 2, or times by a half, so we can write that out the front. Minus 1 on 5, tan inverse of x on 3, but don't forget we have to multiply by a third, so we write that out the front, and then plus c. And I suppose that we can just calculate these fractions, the product of these fractions. So we have 1 on 10, tan inverse of x on 2, minus 1 on 15, tan inverse x on 3, plus a constant. And that is our final answer.